Hello, my name is Jonathan Brewer. I'm a professional engineer at Stress Engineering Services.
And this is Colton Sheets, also a professional engineer at Stress Engineering Services.
Thank you very much for joining us for our webinar on assessing pipelines susceptible to geohazards and soil movement. So the overview of our webinar today is to talk about how permanent ground displacement or geohazards present a significant hazard for buried and above ground pipelines. Um, as a result of these PGDs or permanent ground displacements, geohazard assessment and monitoring can be critical in managing the safe operation of a pipeline system during just normal operation as well as after known events. Uh, Generally speaking, I'm not a geotechnical engineer, so when it comes to exactly what's going on with permanent ground displacement, we would recommend that you talk to somebody with a little bit more expertise, but we are prepared to talk about general permanent ground displacement and what are the general causes. Generally speaking, they can fall into four categories: ground subsidence, sinkhole formation, slope instability, also known as landslides, and earthquakes. Ground subsidence is the overall long-term settling and sinking of the ground surface. It can happen for many reasons, including compaction of soil after construction, changes of the soil moisture content, dissolution of soluble rock below the surface, or collapse of below ground structures. In the two pictures that we show here, the first one on the right is the Leaning Tower of Pisa. This was actually due to compaction of the soil underneath part of the slab that it was installed on. And then on the left, you can see that there's a collapse of a cave, which can cause basically a trough of ground subsidence to happen. If your pipeline happened to be over that cave, you could have some issues with the overall acceptability of your pipeline. The next category is sinkholes, and the sinkholes are a little bit more, generally they happen a little bit quicker. They are and they're only really an issue in specific areas. Generally, they are caused by many of the same reason as ground subsidence. They can be natural or man-made, and they're generally in four categories, which is solution sinkholes, cover subsidence sinkholes, and cover collapse sinkholes. Generally, those three categories have to do with exactly the way the sinkhole forms and how quickly it forms. There's a couple examples that you can see in the pictures below. The first one on the bottom left is the Great Blue Hole near Belize City. They do a lot of free diving in there. It's below the ocean and it several hundred feet deep. The one in the middle is a Guatemala City sinkhole that happened after Tropical Storm Agatha, because sometimes these can be formed by large storm events. And then on the right, we have a picture in Tampa Bay of a sinkhole forming in somebody's backyard and actually starting to eat up their house. So imagine your pipeline in any of those situations could be very, very bad. Another area that has been subject to a lot of sinkhole formation recently is in Louisiana. In Bayou Corn, Louisiana, a sinkhole formed because they were doing salt mining, and the edge of the salt mine started to collapse, leading to a large sinkhole formation, and the sinkhole has been spreading over time. And what you can see here is the drastic spread of that sinkhole, and you can actually see these trees starting to sink into the sinkhole. This is actually kind of a good example of how deep these things can be and how fast they can form. And you can see there the entire height of those trees is eventually going to be eaten up by this lake that has really formed as a result of that sinkhole formation. Slope instability is generally referred to as a landslide, and it's defined as the movement of mass, rock, debris, or debris down an earth slope. They are caused by either sudden or gradual loss of slope stability. Often it's caused for natural reasons, such as extreme rainfall or earthquakes, but the severity and likelihood is exacerbated by construction activity, such as loss of vegetation on the slope, or if you're cutting into things that would be otherwise protecting it from water movement. But you can see on the bottom left, we have a large landslide that has actually a large section of a hill in Cusco, Peru. And then on the right, we have a landslide that's going over a road in Nashville, Tennessee. Generally, in the United States, we saw a lot of landslide risk in the Appalachian area. The last category is earthquakes, and permanent ground displacement caused by coseismic fault displacement does present a significant hazard for buried pipelines. Large displacements are infrequent from earthquakes, but can result in pipeline buckling, rupture, or subsequent failure. You can see on the bottom is actually after an earthquake in Anchorage, Alaska. So movement due to the fault displacement can be damaging. However, earthquakes can also result in landslides or formations of other types of permanent ground displacement. So really, if you have a pipeline in a region that is subject to earthquakes, you have to be very careful in making sure you understand all of the geohazards in the area. So managing the risk associated with geohazards and soil movement really is a three-step process. The first step is hazard identification. The second step is to assess the effect of the geohazards on the pipeline, in which this is really defining the stress and strain demand and the allowable stress strain capacity of your pipeline to try to figure out if you have soil movement, what is the likelihood of failure? And then the third step is to implement risk mitigation measures if necessary. Hazard identification is typically performed by geologists or geotechnical engineers. Really, what it involves is reviewing the pipeline's route to determine what types of soil movement and the magnitude of soil movement that's likely in a region. What you can actually see on the right is a table from a publication by Stress Engineering and Golder, which was an earthquake risk management paper, where you can actually see for given faults, we have defined the probability of set distances of soil movement. And this really was the input for an assessment to determine the risk of a pipeline operating. Uh, Really, the hazard identification can include estimating that probability. If possible, really, if you're looking for a quantitative assessment of risk, you need probabilities for given levels of soil movement. The second step is to assess the effect of geohazards. Once you've identified the magnitude and probability of soil movement, those two things alone can be a good indicator of the most critical areas of a pipeline. However, detailed analysis is still necessary because a given level of soil movement, depending on your pipeline properties, your pipeline geometry, your pipeline route, really all of those things may mean that soil movement in one area may not be as severe as soil movement in another area. So the way that we assess this is we actually perform detailed analysis of these pipelines to figure out how much strain or stress is generated in the pipeline system as a result of known distances of soil movement. Now, this is combined in essence with the probability of soil movement to create a plot like we see on the right, where we have the tensile longitudinal strain as a function of the probability of exceedance of soil movement, or the probability of exceedance over 50 years. So you can see that as you go lower on that probability of exceedance, the likelihood of given levels of tensile longitudinal strain increase. Now, the analysis that you do should account for the pipeline geometric features such as bends and valves, site-specific soil properties verified by testing, and then the measured pipe properties if available. You can use specified minimums, but really you need to be using for this type of an assessment the measured pipe properties to get the best results. Once the analysis is complete, the results are combined with the strain capacity curves, which Colton will talk about a little bit later, to determine the probability of failure. The strain capacity is a function of the type of strain, whether it's tensile versus compressive, and the pipeline geometry, including the D over T, the loading conditions, the material properties of the pipeline, geometric imperfections, the weld geometry. Those are just a couple of the things that they are dependent on. Among those also could be the year that it was manufactured, as well as inspections that have been done to determine whether you have flaws in the pipeline already. Some standards do exist for determining the strain capacity. However, pipe-specific testing is recommended and may be required to accurately define the capacity. The last step is risk mitigation. And really at this point, if the probability of failure is too high, the operator can mitigate the risk in many ways. Most of the mitigations fall into one or more of the categories here. The first is to decrease the strain demand on the pipeline. Really, this can be done by changing the design of the pipeline, relocating the pipeline, increasing the strength of the pipeline. Some of these are really only available if you figure out what the risks are before you actually install the pipeline. However, if you've already installed and you're dealing with a pipeline that's already in place, you might still be able to do this by basically excavating the pipe in the area of concern and using a different backfill so you can minimize the strength of the soil in that area. The second is to increase the strain and stress capacity of the pipeline using a higher grade or tougher materials. Really, that is only an option for new pipelines or if you're going to be doing very modifications or cutting out the regions of the pipeline. The third thing is to monitor the pipeline. So you can install strain gauges on the pipeline, or you can install things to monitor for soil movement. The monitoring itself does not necessarily change the risk of a failure. However, it does let you know what's going on. So for instance, if it was something that was caused by soil subsidence generally isn't happening quickly. So it may be enough to just monitor the pipeline and look for those changes to identify when risks are starting to become more severe. And the last thing is to address the consequences of failure by planning. Really, this is modifying emergency response procedures, installing isolation valves so that if you do get a failure, maybe you can just reduce the ramifications of that failure or reduce the volume that's lost. So one case study, and this is just a study of one that we're doing some monitoring on, is a pipeline operator that we're working with identified a potential pipeline loading due to soil subsidence around a levee. The levee itself is anchored in bedrock, so the levee is stationary while the soil around it on the left and on the right is subsiding. So you can actually see that on the picture below on the downstream and upstream side of that pipeline, the soil on either side of that and the concrete levee is right in the middle. There's actually a hole through the levee that the pipeline passes through. And as that soil displaces on either side, it's causing that pipeline to be bent over the levee. So the pipeline operator wanted to evaluate options for protecting the pipeline. Monitoring the pipeline to determine when replacement became necessary, as well as determining the effect of excavation and other reasonable mitigation measures. So what we did is we built a finite element model using Abacus general purpose finite element code. The model that we built included approximately 3,000 feet on either side of the levee so that we don't have effects from the in boundary conditions. And then we used a combination of beam and shell elements on the model. The beam elements are in the buried portions. The shell elements are right around the levee. And the effect of the soil on the pipeline is defined using pipe soil interaction elements. So you can see an overview of the FE model that we generated here. The orange sections that look like little wedges here on the left and right are the pipe soil interaction elements. We have black shown here as the beam elements, and then the gray is actually shell elements. And then we have a couple rigid supports in the system, which are actual supports that are in the field. The analysis steps that we did, the first is we applied gravity and internal pressure to the pipeline. The second step was to introduce the pipe supports with no applied support load. So this kind of gives us the as-built situation for the pipeline where really the supports are there, but just barely touching the pipeline. And then we started to model soil subsidence to see what the effect was on the stress of the pipeline. And then the last step was to model the pipe excavation. So the soil is removed from both sides of the levee in small increments, monitoring the stresses in the pipe during the soil removal process to see how effective excavation could be on the stresses in the pipeline. So the analysis results that we see here, the x-axis on this is distance from the levee center and the y-axis is longitudinal stress. So the stresses due to soil subsidence, you can see here on the top of the pipe, which is blue, and on the bottom of the pipe, which is red, really do get quite high. And these are all relative values. So they're relatively high at these supports. And then at the sides of the pipe, we do have some stresses, but they're not nearly as high. Uh, but as a result of this, we see that at those supports, those stresses are close to the allowable limits, and we are concerned about that. So let's go ahead and see what the effect is from excavation. So after we do some excavation or digging up the pipeline for a given length on either side of that levee, you can see that these stresses go way down. That before the axis here is from x over 2 to x. When we've removed some soil around that area, we've reduced the stress by about a factor of 2 to 4, depending on exactly where you're looking. So this is a very good mitigation measure for this area. So really, the analysis indicated that soil subsidence does result in high stresses for this pipeline. It also shows that excavating can be used as a good option to reduce the loading in the pipeline. However, for the case that we were dealing with, excavating the pipeline would require considerable time and permitting and may not actually even be allowed because we're around a levee. Therefore, the operator has developed an emergency repair plan to cut and lengthen the pipe, and they're continuing to monitor the pipeline using strain gauges. The analysis results were used to determine the best locations for the strain gauge placement, and the periodic monitoring was performed to see when the stresses, how the stresses were increasing over time, and to figure out if we were seeing something that would be failure imminent. Long term, the pipeline operator is planning on actually replacing this segment of the pipeline so that this is no longer a risk at all. But really, the monitoring that we're doing is in preparation of and making sure that we're mitigating the risks to the pipeline in the short term. So for strain gauge installation, what we did is we looked at the FEA results and we figured out that there were a couple locations that made sense to install strain gauges. Basically, we look at the FE results to see where we have relatively high local peaks in the longitudinal stresses, because those are the places where the strain gauges will be the most effective. And so what we see here, the dashed lines are the pipe supports. So basically we identified 5 locations for strain gauge installation. Basically at each of 3 pipe supports, as well as there's 2 bends in the pipeline around the levee in the blue circled areas. So if we install strain gauges on these 3 areas, we're going to see the largest changes in stress as a function of soil subsidence. So these are going to be the most effective places to install the strain gauges. And this is giving us an example of what this strain gauge installation looks like. For this case, we did install 14 vibrating wire strain gauges at 5 locations. At each of the 2 bins, which I was showing in blue on the previous page, we installed 4 strain gauges around the circumference of the pipeline. This allows us to monitor for bending and axial load. And at each of the 3 supports, we installed 2 strain gauges near the top of the pipe over the support. The 2 gauges allowed for gauge redundancy. In these areas, we couldn't install gauges around the circumference just because we didn't have access. And you can kind of see that on this section in the middle where there's 2 gauges at the top of the pipeline, but really we didn't install any at the bottom because that support is underneath the pipeline. And the 2 gauges do allow for gauge redundancy, and we're also just looking for the stresses in the pipeline over time, or the changes in strain in the pipeline over time, rather than load at that specific cross section. So the monitoring results, really for this case, the strain gauge measurements were being taken every 2 weeks, and that data was sent to stress engineering. The process data indicates that the loads in the pipeline and the pipeline stresses are a function of internal pressure and temperature, but do not appear to be changing over time. Really what that means for us is that the soil movement does not appear to be increasing over time, or at least very quickly. So when you see these contour plots or these plots on the bottom left and bottom right, what these are is the axial stresses and bending moments as a function of pressure. And you can see really at each location, which is a different color, you can see that there is a pretty good linear relationship between the stress and the load and pressure, but they're not really increasing as a function of soil displacement. And really what we're seeing from this is it does not appear that significant additional subsidence has occurred since the gauges were installed. But really, we do need to keep an eye on this over time, because lack of soil movement in the past does not necessarily mean that we're not going to see it in the future. So we do need to keep on this and keep looking at it to see if there's going to be problems down the road. At this point, I'm going to hand it over to Colton Sheets to talk a little bit about strain capacity of pipelines.
Okay, thanks, Jonathan. Appreciate it. So from the case study that Jonathan presented, it's pretty clear that we were able to identify the threat and see the impact on the area of interest, and then quantify that using analysis and in situ monitoring. So now we want to talk about how we can relate that information to acceptability criteria and determine what next steps need to be taken for mitigation or continued operation. So when we're talking about acceptance criteria, in most of the cases, we're looking at permanent ground displacement. We're typically trying to understand what's an acceptable strain capacity of the pipeline. And strain is going to be a function of displacement. So we want to understand how the displacements we're expecting from the PGD compared to the displacement that my pipeline can withstand before a failure occurs. So in other words, we want to know if the displacement from the PGD is less than the displacement required for failure. So for example, is that acceptance criteria at 0.2% strain, at 0.5% strain, or even at 2% strain? We need some value, strain value, that we can tie back to. And so for a lot of assessments that we do, we can relate that back to some acceptance criteria that is generally accepted by industry. Either that's a code or a standard or some general accepted practice. With geohazards and PGDs, there isn't necessarily a standard acceptance criteria that can broadly be applied. If we were to try and go extremely conservative, that might not work for us either, as even a minor PGD could lead us to exceeding those conservative limitations. Since we're typically dealing with the potential for very large displacements when looking at a PGD type scenario, a lot of work is focused on using strain-based design for these applications. And then strain-based design is often used when strains are expected to exceed 0.5% strain, and it relies pretty heavily on coupon level and full-scale testing. And testing is a major component of strain-based design because we're trying to determine the performance of specific pipeline materials and also the performance of the girth welds that are used in the design and fabrication of the pipeline. And this testing is ideally completed during the design stage before the pipeline is installed, but we can also do it retroactively after installation if there's enough material remaining from construction. So I want to talk a little bit more about the testing side of strain-based design and how they can be used as a tool for determining the pipeline performance. And it's important to remember we're trying to determine the strain capacity or how far a pipeline material can displace before failure occurs. So just as a side note, the reason that I've mentioned girth welds as part of the strain-based design is because that's a critical area for these assessments. Girth welds are more likely to have a flaw than the base pipe material, and they can also be misaligned during installation or could potentially have different material properties as well. So going back to the full scale and coupon level testing, they basically compose the two primary methods for testing. So for coupon level testing, we're going to think small scale on the order of a tensile test. And for full scale testing, we're thinking more large scale. So a full size pipe, often using really high loads and can accommodate much larger pipe sizes. So I'm going to briefly talk about each testing method, and I'm going to start with the coupon level testing. So I have a picture here on the right side of the slide that shows an example of a coupon level test. For strain-based design, these are typically called curved wide plate tests. And essentially, it's a section of pipeline material that's subjected to a tensile test. So in this test, what you're looking for is the strain to failure, which can be captured using the test frame, and then that's going to help you determine the criteria for the pipeline material. So the advantage to this type of testing is that you can do several tests and get several data points using less material, so it's typically more cost effective. The downside is that you don't get to capture the effect of things like internal pressure on the strain capacity of the material. So on the other end of the scale, we have full-scale testing. And again, this is typically much larger scale using full pipe samples. And what we can do is subject these full pipe samples to a variety of load conditions, whether that be tensile loads, compressive loads, or bending. And we can do all of these different load combinations while simulating internal pressure in the pipe. So we get that full combined loading condition. So for many of the pipelines out there that we're going to be applying these loads to, they can be on the order of several million pounds or even several million foot-pounds of bending. And not only can we recreate the load conditions, but full-scale testing also allows us to recreate and simulate different fabrication and flaw conditions that might be present. These could be girth weld offset, some type of wall loss, or even a crack-like feature. I have a picture showing a simulated wall loss defect on one of our full-scale test samples there in the bottom right. And then also in the top right photograph, you can see a test sample that's loaded in one of the test frames we have at Stress Engineering that we use to apply the tensile loads. Now, the downside of full-scale testing is that it requires larger scale, more complex equipment and instrumentation. So that means that it will be more time consuming and typically much more expensive than the coupon level testing. It kind of reminds me of the scene in Jurassic Park where the kid picks up the night vision goggles, and the guy says, "Are they heavy?" Then they're expensive. That's kind of the same with full-scale testing. So while we're doing all of this work, and keep in mind we're trying to capture the strain response of the pipeline when it's undergoing these full-scale loads or coupon level loads. That's what we're after, and that strain capacity and strain response is what we're going to be using to determine our acceptance criteria. So in full-scale testing, we can do this in a variety of ways. For a more global measurement of displacement, we can use displacement transducers. And the photo in the top right of this slide shows several displacement transducers that are installed on a pipe sample. And then for more localized strain response, we can use strain gauges. These tests often exceed the limits of typical strain gauges. So what we can do is also use other techniques like digital image correlation, which can monitor strain, local and global strains, real time, all the way up to the point of failure. And so we have that capability at Stress Engineering Services. There's a photograph in the bottom right hand side showing a simulated wall loss defect that's using DIC to capture the strain response under load. So again, what we're using these tests for is to give us the strain capacity of the pipeline of interest, and then we're using that to determine our acceptance criteria. So if we look at the plot on the right, which is a plot of applied load versus axial strain all the way up to the point of failure, what we're going to want to do is find a point on the x-axis that we know is achievable for our pipeline, and we're going to set that as our acceptance criteria. So if you looked at setting the green dashed line as your acceptance criteria, which is about 2% axial strain in this condition, strains to the right of that level would be unacceptable, and strains to the left, strains to the left would be acceptable, and strains to the right would be unacceptable. And then we can use this information in our comparison back to our analysis, such that similar to the analysis that Jonathan performed, or the in-situ monitoring that we're conducting, so where we've gone out in the field and installed those remote strain gauges. So wrapping up here with the final summary, we talked about PGD, which was permanent ground displacement, how it's a geohazard and how it can impact pipelines. We talked about the process of assessing a pipeline that's susceptible to geohazards, how a combination of analysis and in-situ monitoring can be used to assess the severity of the issue that the pipeline may be experiencing, and then how the results can be then compared back to testing, whether that be coupon level or full-scale testing results, and from those determine an acceptance criteria. So thanks again for your time. We hope that talking through this process has been beneficial to everyone, and now we'll be answering any questions that were submitted during the presentation.